Okay, hello, good morning. Jumping into the derivatives of log functions today. So we've looked at the derivatives for basic inverse functions in that quick reading that we have in the module. And today we're going to look specifically at log functions, which are the inverse to exponential functions. I'm going to do a quick review because I think these properties of logs are not always front of mind for us coming out of pre-calc, and it's very, very helpful. Log functions are huge in that they are the inverse to exponential functions, and exponential functions in themselves are huge, especially in engineering, differential equations, things like this, biology. So having command over these is going to be important. And so what I'll do is we'll first review the properties of logs, which might seem boring or just kind of math facty, but it will very much help you to commit these to memory so that you're not reinventing the wheel when working with these things. I'll show you the derivations quickly of where these derivatives come from. Again, just to kind of show you how math works, how mathematicians think and come up with these things, or discover these things. And then we'll look at a cool example, I think, at the end of an application of this, which for those of you going on to differential equations will be highly relevant. So, um, first of all, looking at log functions in general, remembering the definition of what a log is, it undoes exponentiation. So log base b of x means that b to the y equals x, right? So x is the power of b that gets you y, is what this what this says. Okay, x is the power of b that gets you y. So we usually use a common log, which is base 10, or natural log, which is base e, which we use ln. We're going to use ln a lot. There's a lot of reasons for this, but it's, since we use e a lot to represent exponential growth and decay, we're going to use ln to undo that. All right, so there's a lot of reasons, but that's one good enough one for you. So you'll see common log is just written as log. You'll see ln written as ln, and if there's a different base, which we'll talk about, some base b, which can be really any non-negative number, or any positive number rather, then you just write it in the subscript. Okay, it's rare, but it does happen. So the basic properties of logs, and these are things that were actually memorized by engineers straight away back in the day, back before we had such powerful computers in our pocket. But this helped them move around gigantic and really small numbers at the drop of a hat. Guys using slide rules could, probably still rival how fast you can make calculations on your calculator now. But anyway, the rules are as such that if you have the product of two factors inside of a logarithm, you can split that apart into a sum of the logs. Again, this is kind of akin to that idea of like, e to the m times e to the n is equal to e to the m plus n. We can kind of split those exponents via sum. Likewise, for quotients, it becomes the difference of the logs. If you have a power within the logarithm, that exponent can be brought out in front as a scalar. This is big. So if you have log of 5 squared, this is really 2 times log of 5. I know sometimes having variables can muddy the water. And then the change of base formula, we'll also use this, that if you want to change the base, let's say I had, log base 4 of x, and I wanted to change this to natural log, log base e. So that'd be the natural log of a, this inner piece, the natural log of x, all over log base b, so natural log of the base prior, so ln of 4. Okay, so this would be changing base. Let's say we don't want to deal with log base 4 anymore. We want to move to natural log. This is how we would represent that. Okay, so it kind of like your trig functions. There's many ways to write it and get around and have the same expression. So we're going to use that to our advantage to make life easier for ourselves, as always, not harder. So how do we differentiate these things? And again, what is the point? The point is to be able to study the instantaneous change. Uh, First, I'll show you quickly how we come up with the derivative of the natural log of x. This is in that note that you saw before using the uh, inverse idea. And I'll show you kind of a quicker proof here. So if we look at this here, you have to remember that e to the ln x, this is the function composed with its inverse, which always gets you back x, which we saw in that last note as well. You know, in general, that f inverse of f of x gets you back x. It's like a round trip, right? You start with x, you go out on f, you come back on f inverse, you start right where you end right where you started. So what we're going to do here is kind of creatively use this fact and not simplify it, and then differentiate both sides to see what we get. Okay, and the secret mission is to be able to find, we want the derivative of ln x is something. This is what we're after. And so we're going to use implicit differentiation here. So on the left, derivative of x with respect to x is just 1, right? And then we'll get the derivative of e to the ln x times the derivative of that inner function, because it's not e to the x, right? It's times the derivative of ln x prime, which we don't know what that is, but we can just write it in this kind of placeholder fashion here. And then we see, okay, well, 1 equals the derivative of e to the ln x is really just, right, e to the ln x. We get back what we had times the derivative of the natural log of x. And this is just because derivative of e to the anything is e to the anything. And we have the derivative of the inner function there. So now here we can kind of undo our cheeky, pretending that this was something something a little bit more complicated. E to the ln x is really just what? It's really just x times ln x prime. And so then if we just go ahead and solve for ln x prime, or the derivative of ln x, we see we just divide both sides by x and we get 1 over x. And so this is actually the rule for the derivative of ln x, or the natural log of x. So we got there very simply, just by using this fact about inverses here. Okay. So to put a like a quick example here, let's say find the derivative for f of x equals, let's say, ln of 3x squared plus 6x. Yeah, let's keep it simple here. So find the derivative for ln of a polynomial. So f prime then is the derivative of the outer function times the derivative of an inner function, right? Because we see I have natural log is on the outside, but on the inside is this 3x squared plus 6x. And so we take the derivative of the outside, which we say is the natural log derivative, 1 over x. So it'd be 1 over 3x squared plus 6x. Remember, we don't change that here. It's evaluated at that output. And then times the derivative of the inner function, which is 6x plus 6. Okay, so then to simplify this here, 6x plus 6 over 3x squared plus 6x. Maybe we could be a little bit nice and factor out 3 from everything. So we'll get 2x plus 2 over x squared plus 2x. It's about as nice as that one gets. Okay, so here we just had a natural log with a chain rule. excuse me, you can obviously mix this up with all the other rules and functions we've studied so far, and I'll have hopefully a practice set after this lecture. So that's using the natural log derivative. Now I wanted to show you where the derivative of the general log function comes from. And I'm going to cheat a little bit and just use what we know. Well, we know that the derivative of the natural log is 1 over x, right? So if we start with log base b of x, we know from our previous page that if I wanted to change base and represent this a different way, I would write this as the ln x over ln of b. And so then if I differentiate both sides with respect to x, okay, on the left I'm looking for the derivative of log base b of x. I don't know what that is, so I'm going to leave that as such. And then on the right, it's really the derivative of the natural log of x times 1 over natural log of b. B is a constant, so this is really like, it's like 1 over 5 or 1 over 10. This is just a constant fraction out here. It's like a scalar. So I'm really just taking the derivative of the natural log times this number, 1 over ln b. And we already know the derivative of ln x. It's 1 over x. So this too is not a part of the presentation. 1 over x times 1 over ln b. And so that's why you see this written as 1 over x ln b for that base. So written more succinctly, the derivative of log base b, any base, 2, 7, 49, is 1 over x times the natural log of that base. That's an easy way to get there. Okay, so that's for 3.2 there. Okay, so that's the derivation of it. So, for like a simple example, maybe we'll do this. Find f prime of x if f of x equals log base 5 of 6x squared. Okay, so again, we have a chain rule here, an inner function. So the derivative is going to be 1 over what's inside that interior function, 1 over 6x squared. And this is times the natural log of 5. However, since we differentiated an outer function and there is an inner function, we need that inner rate of change. And so that will be times 12x, right, because of the chain rule. And so this all simplifies to, 12 over 6 becomes 2. The x cancels up top, and so it'll be 2 over x ln 5. Right, and so that's about as simple as it gets. All right, we'll have some more worked examples on using these with all the rules that we have. And the last thing I wanted to do was give you kind of an application here, again, to frame why it's important at an entry level. So we have a cool population growth model, which again comes up as one of the primary things we study in differential equations. So it's kind of cool that you get to peek ahead into something that's a much higher level, but it's happening right now. So I'll just kind of read through this with you. So we're applying the derivative of log functions to a population growth. This is a common formula to represent population growth. It's unbounded, so it's not the logistic equation, which you might have heard of or seen already, but it is a very good model within a reasonable window. So P naught is your initial population, E is the natural base, K is your growth rate, T is time. And so, if we wanted to find dp dt, one way we could do this would be to use logarithmic differentiation, which I will actually show you I'll show you how to do this afterwards as well. But the idea is if we take the natural log of both sides first before differentiating, we get something kind of neat, which is we're able to use this natural log property to split up the equation. So on the right, you can see we split that product into natural log of P naught plus natural log of e to the kt. And then this, we use a property here about of ln e to the x being x, right? That when you compose a function with its inverse, you just get back the input. So that simplifies the right-hand side so that we're just left with a plus kt over here. And now if we differentiate both sides, what happens is that on the left-hand side, we use the chain rule. So we get 1 over pt times the derivative of pt, p of t rather. And then on the right-hand side, we differentiate natural log of p naught. That becomes 0. And we differentiate kt, and so we're just left with k. Okay, p naught was just a constant. But here, this is like a linear function, so when you differentiate it, you just get the slope. And so then you're left with 1 over p times dp dt equals k. And then if we solve for dp dt, what do we get? We get this is equal to k times p of t. So this is very interesting in that you have an equation in which you're relating p, the amount, and its own derivative. And so this is what we call a differential equation. It's the most important and simplest differential equation that we have. And so what it really means is that the rate of change is proportional to the amount that you have. And so this this equation describes perfectly what an exponential growth or decay looks like. It's based on how much there is, right? 7% of what's in a millionaire's account is different than 7% of what's in your account. It matters how much is in the account, right? It matters how many people there are in the population. So things like this. All right, so this is a cool application, I thought, to bring up, and again, let you guys preview something that's kind of an advanced idea. And the last thing I wanted to show you as well, kind of like a bonus, is what we call logarithmic differentiation. This is a technique of using log to find the derivative for something that's relatively complicated. So let's say that, you know, you're given y equals, I don't know, 2x plus 1 to the 7/4 times x to the 31st. Okay. You know, you can use the product rule here. It's actually not so bad, but I want to show you kind of a different way to go about it now that you are armed with this tool. So instead of just differentiating straight away, what we can do is what we saw in that application, which is take the natural log of both sides first, right? If you have equality, then applying the operation to both sides means you're preserving that equality, so it's all legit. So what we get is ln of y on this side equals the natural log of all this stuff on the right. And so we know from that property of logs that we can split this product into a sum of the logs. And again, the goal here is to make life easier, not more complicated. So splitting this up actually is simplifying the problem. We can use that power rule of logs again to bring the exponents down in front. So we get 7/4 ln 2x plus 1 plus 31 ln x. Notice, ask yourself, has Mally done any calculus yet? No, he has not, right? This is only algebra. So now that we're here and we've got a pretty nice equation involving logs, now I can differentiate both sides with respect to x. All right, and so then we get on the left, you know, the derivative of y. Well, y is really a function of x, so we will get 1 over y, but then we'll need to respect the chain rule dy dx. equals, and then on the left, these are all ln derivatives, so they're pretty simple. So 7/4 times natural log, the derivative of natural log of 2x over 1 is 1 over 2x plus 1 times 2, right? Because we had this inner function here, plus the derivative of 31 ln x is 31 over x, right? 31 times 1 over x. And so we'll simplify a little bit here. 1 over y dy dx is, let's see, we got a 2 to cancel with this 4, so we'll get 7 over 2 times 1 over 2x plus 1 plus 31 over x. All right, and then one thing that you can do here is then take y, right? You know that y equals 2x plus 1 to the 7/4 times x to the 31st. You can take this fact and substitute it back in for y, okay? And so this becomes 1 over 2x plus 1 to the 7/4 x to the 31st times dy dx equals the right-hand side. And then to solve for dy dx, we are just multiplying both sides by the reciprocal of this. So we'll be left with dy dx equals 7/2, 1 over 2x plus 1, plus 31 over x, all times 2x plus 1 to the 7/4, x to the 31, all over 1. Okay, and so we can simplify from here. And so, you might be asking yourself, like, this maybe looks more complicated. This, I made this example up off the fly, but when you have lots of exponents and products of things with a lot of exponents, this tends to be an easier way to go instead of maybe doing like a triple product rule, something like that, right? So it definitely has its place to simplify. But, oftentimes it's not super clear what is the most efficient path, and that's okay. If it's, a tie, any technique or method will take you to the desired result as long as no rules are broken. So you also want to, figure out, where am I going to make the least mistakes, right? What methods am I most comfortable with, and stuff like that. So here, and I don't think I wrote this in, given this, we want to find dy dx as our prompt here. So that is what I wanted to cover today. So, you have now the derivative for ln x, and for the general log function of base b is 1 over x ln b. Add these to your notes sheet, add these to your repertoire, and have fun tackling some new exercises as well as some applied problems.